Good afternoon, all participants. A hearty welcome to all of you on the last session today. On behalf of the Basic Science and Humanities Department, I welcome all the participants and the resource persons. The speaker of the day is Dr. G. Santosh Kumar, Professor, Department of Computer Science, Cochin University of Science and Technology, Kochi. Is a versatile personality with a grounding base in physics and moved on to become a computer scientist. Over to Lija for a small introduction of the speaker. Lija, please.
Thank you, Meena ma'am. Good afternoon to all. It's a moment of great pleasure for me to introduce the resource person, Dr. G. Santosh Kumar, Professor, Department of Computer Science, Cochin University of Science and Technology. His broad areas of research are cyber physical systems, computer vision, natural language processing, etc. He is here to enlighten us on mathematical perspective of data science. He has completed his MSc and MPhil in physics and MTech in Computer and Information Science from Cochin University of Science and Technology. He took PhD from CUSAT in 2011. He has worked at Infotech SDN Malaysia and Tao Information Technology Bangalore as Senior Analyst Programmer. Then he joined in Department of Computer Science of CUSAT in 2001. He was head of the Department of Computer Science of CUSAT for the last 3 years. He was member of Board of Studies, Aeronautical Science and Technology, Cochin University from 2014 to 2018. At present, he is the chairman of Board of Studies, Computer Science, Cochin University. He is a member of Senate of Cochin University from 2017 onwards, a member of Board of Governance and Executive Committee, CDIT Trivandrum, Director of Center for Information Resource Management, Cochin University from 2015 onwards. He is a senior professional member of ACM, senior member of IEEE, and a life member of CSI. He is a project investigator, Spark project of MHRD, India. He has published research papers in several national and international journals. He is associate editor of several reputed journals. We are looking forward for a great session from you, sir. I request Santosh sir to kindly take over. Thank you.
Yeah, thank you. So good afternoon. Thank you, Meena and Lija. Thank you for inviting me and giving me an opportunity to interact with great people like you. So I'll be presenting mathematical perspectives of data science. So I hope you can see the presentation.
Yes, sir.
Okay, thank you. Yeah. So basically, this FDP, as I understood from the brochure, was concentrating on various aspects regarding an emerging field called data science. So the organizers actually rightly jotted down the topics for understanding this emerging field of data science, which is basically a fusion of many other disciplines, including statistics and computer science. And this field is actually benefiting a lot of arenas, not only in computer science, but a lot of other related areas. It's like in business also, it is contributing a lot. So today, I'll be sticking on this agenda. So I will spend some time on these aspects. So my perspective will be from computer science angle, because most of the time I was spending to do some practical uh, implementations of already known algorithms and maybe the techniques. But the mathematical underpinning is very, very important. Without that, nobody can understand actually what happens when you run an application and see the results. Unfortunately, many of the, uh, I would say, many of the computer science people tend to use a lot of tools uh, which gives a lot of libraries which already been implemented many of the algorithms uh, without knowing basically what happens inside the function that is being called. So for a computer science persons, this talk will be useful. Uh, I understand that many other disciplines also there, so I will try to satisfy persons from all disciplines. So let me start with uh, the field data science. So basically, this entire field is not actually not new actually. Uh, it was there for a long time in the name of data analysis. Basically, when computing power or computation power was available to people and enough data was available, uh, then computer can do a lot of number crunching kind of jobs, and basically people try to look into the patterns that exist in the data set. Otherwise, it's not obvious actually. So by patterns, basically what we mean is the underlying connections between the data, the underlying correlations between the data. So these kinds of correlations and this type of patterns, basically it's not obvious because of large uh, data sets. And the computation aspects also is nowadays different. So the subject actually moved from data analysis to a flourished kind of a uh, topic called data science. So largely, while dealing with data science, we are interested in science of data. So large scale aspects of data and how we can do computations on these type of large data sets. So one important aspect is uh, of data driven science. So as we know, data, basically science subjects like physics or chemistry or mathematics for that matter, uh, people do a lot of intellectual contributions. So they come up with some formulas and equations based on their intuition, observation, etc. But now huge volume of data is available. So can we engineer or re-engineer something from the generated data? So this aspect is very important. So for example, the Human Genome Project, basically some 20 years before, the first result of human genome sequencing was announced. So that paper was published in Nature. And huge volume of data was available to the people or scientists to play with. Now we actually reap the benefits of this project. because we can now understand basically what is happening when two genomes are basically interacting, DNA sequences are interacting, why a kind of a mutation basically has happened. A lot of information is available now. So basically this was due to the huge data that was available as a result of this project. People can do some drug design, drug delivery systems, etc. People can design personalized medicines. So all these aspects were actually happened due to the availability of data and the analysis, computation analysis power that is available to us. It's not just a single machine holding a bunch of data and people start applying some algorithms and see the results. It's a huge distributed system where you store data in varieties of systems, and an algorithm actually coordinates the task and brings you the results. And geographically distributed scientists can contribute. Even if you read the history of Human Genome Project, you will see that large number of people from varieties of labs contributed in a distributed manner. So this was actually possible due to the networking and computational aspects of our internet and availability of these facilities to the whole community. So another example I just wanted to tell you is about 1995, Google has announced their search engine. Until then, basically people are sitting and curating the keywords, and based on those keywords, the search engines were actually giving the results. Google has automated the entire process. Basically, they come up with a very versatile algorithm called page ranking algorithm. So it ranks, considering a lot of factors. It ranks the each and every web pages that is available in the World Wide Web, and basically it throws millions of pages across a search term, and most probably the first few pages are the pages that we are actually intending to look at it. So this was possible basically due to the distributed nature of computation and the availability of the huge volume of data. So basically, from the birth of www, basically it contains billions of web pages now, and in varieties of ways we can process it in terms of text, in terms of images, in terms of video, etc., etc. So all this has happened due to the availability of huge data and the computation process. And in data-driven aspect, data-driven science aspect, basically what we do is we try to tackle inverse problems. Basically, some physical phenomena has happened, and this physical phenomena, let's call it, it's a process. A process has happened, and this process has generated a lot of data. And we can only record the data from this process or the experiment. And we are actually trying to figure out what is the basic distribution from which this data is actually being generated. So we are trying to solve the real settings of the problem by getting the data and doing an analysis on the data, right? So this is called an inverse kind of problem. And interestingly, most of the real world problems, you can see that most of them are inverse problems. So when we take a photograph, for example, right? So we have an image as a result. So image, you can just consider it as a group of pixels, which was actually generated by the CCD arrays of the camera. So it basically records the intensity values of available to it. It is being recorded. So from which distribution or from which mixture of distributions actually these intensity values are actually being originated, and uh, basically while we are recording, there will be a lot of noise that will be coming up, and we have a handicapness of collecting everything. So the camera itself has a limitation in recording all the intensity values. For example, the real world is an analog system, and in your camera, most often it's a digital camera, and you sample it and then store it. So there is a possibility of losing a lot of information, and there is a possibility of incurring noise in the system, right? So you have only a bunch of data, which is not actually the exact replica of that phenomena or the process that has happened. Plus, you have a lot of inherent plus additional noise that is blended with the data. So with this type of noisy data, how you are going to model, or how you are going to model the entire process, so that you understand something about the physical process that has generated this type of data. So this is very important. So here data science related tools and techniques will help you out in dealing with this type of inverse problems, and it helps modeling such phenomena. Another aspect is about optimization. Basically, you might have heard about machine learning algorithms, which usually wants to find a function. Basically, it looks for a function which generated the data, and the machine learning algorithms actually maybe guess some functions, and your duty is to check whether the machine learning algorithm generated function is similar to the, or how far you are from the actual function, right? So a lot of optimization techniques we use, because exact answers you cannot it's not possible to find out exact answers. You can only get some optimized results. So as a background setting, I just wanted to tell you about the importance of data science, and in fact the math behind the data science, and the computational aspects behind the data science. So statistics people will say that okay, the underlying principle of data science is statistics. Yes, I do also agree, but a lot of computational aspects are coming up, and how to deal with this type of huge amount of data uh, is a computer science aspect. So let's have a mixture of all the aspects from different varieties of fields. So that we call data science is a combination of, or is a maybe contributed from, the ideas are contributed from different. So my idea here is to expose some basic problems which involves these type of data-driven analysis and trying to understand the data. So I will expose to you these type of applications, and I will try to explain the mathematical aspects behind the scenes. So I will just I will tell you the data science life cycle. Basically, nowadays the heavily paid job in IT industry is of that of a data scientist. So these are the basic duties done by a data scientist. So these are the major blocks, building blocks of a data science life cycle. So it involves capturing the data. So basically, you want to extract data. In between, you just wanted to maintain it in using different techniques that's developed in computer science. Then you want to process it using different techniques. So data mining is basically is a heavily used tool to understand what is basically involved in the data and finding out the patterns. And clustering as well as classification are the major set of problems that we address nowadays. So once we get data, basically you should understand there are varieties of ways we can capture data. One way is just to capture the data as it is coming. You call it as an unstructured data. For example, suppose you want to collect the data from World Wide Web, for example. It might be it's not purely a structured format, but a semi-structured format is there. So if you are collecting HTML pages, for example, for text analysis and classification, then you call it as a unstructured or a semi-structured kind of data, or old-fashioned data base concepts. It's you can collect data and structure it like a table. So in that case, it's a kind of a maybe a structured type of data, and within that you can have a data set with labels. That means once you collect data, you can label that data. So you can attach a label to a string of data. So that can be used for a supervised kind of learning. And there is data which is not actually labeled. So we call it as an unsupervised kind of a learning will be required to deal with those type of data. So data modeling and data summarization is again the process. Then you do a lot of analysis based on data. So most of the times people would say that what is the ultimate goal of data science? Basically, it is generating some actionable insights. So in a business world, for example, a company is driving some business, so they do collect a lot of data from their customers, and then they want to do an analysis and want to see basically what kind of insight can be drawn from that, and how they can improve their business strategies. So a predictive kind of analysis is basically done. Then mining regression. Basically, here we try to come up with the latent patterns in the data. So latent in the sense you cannot directly measure it. You just maybe you can observe the phenomena and then try to understand what actually been generating this type of data, and you can see the patterns in the data, right? And then communicating the data. So this part is basically with visualization and reporting and building business intelligence, etc. So now I will spend some time on data and its representation. Um, this is also very important because in the first spell of your FDP, you have learned a lot of facts about vector space and linear algebra. So how this linear algebra is basically used in a problem which pertains to the, and I will try to highlight the importance of embeddings basically. So let's take a simple problem. So it's a given a set of documents and some query. We need to retrieve relevant documents that are similar to the search query. So this is a very classical information retrieval problem. Uh, so here, how we can bring in the concept of linear algebra and how we can use that concept to solve this problem. So this is the intention of highlighting this problem. So it's a very novice or very fundamental problem that is been solved elegantly. So we use vector space model. So here you represent the text documents into a vector of words, and followed by that you transform the numerical format so that we can apply a lot of techniques to figure out what is actually hidden in input. So let's try to understand this with some examples. So you have a bunch of document, right? So these are bunch of documents. Let's just assume a very simple statement. Document 1 contains cat runs behind rat, and document 2 represents dog runs behind cat, right? So this is the entire universe of documents I have, and the query actually been coming as a rat. So this is also a term uh, which must be searched against this entire universe and find out basically which document is basically similar to this query, so that the user can click that document and see the occurrence of rat there, right? So one step is, this is a whole bunch of document and you need a lot of pre-processing. So for example, suppose you are downloading this document from World Wide Web. So you need a lot of pre-processing, and basically I have done some pre-processing. Pre-processing is basically you just omit some frequently used small keyword text, then full stops, semicolons, etc., etc. So after that, you have a refined document which contains words. So document 1 contains these. So maybe fortunately, unfortunately, there is no stop words or something to be pre-processed here. But let's understand there is a lot of in, a, the type of words or stop words, exclamation marks, etc., etc. Those kinds of words can be characters can be removed from the document. So you get these two documents. So now we have represented this as a string of words. Now we wanted to process the relevance of the document against the query. So which document contains the keyword that user has given. So how we can do that? So this is a very fundamental idea: term frequency, inverse document frequency, TF IDF. So word which occurs in most of the documents might not contribute to represent the document relevance, whereas less frequently occurred items might define the document relevance. So there might be a lot of repeated keywords in the document, but we are going to search for a particular keyword, and we are trying to make the relevance of the, or figure out the relevance of the document. So let's try to understand what is this. Term frequency is the number of times a term occurs in a document, and inverse document frequency can be calculated like this. So inverse document frequency is log n. N is the total number of documents, and document frequency. So DF is number of documents containing a term. So I have illustrated this with this example, a small example. So you can see that document, we had two documents, document 1, document 2, and the query term. Right? So cat was occurring document 1 and document 2, and the query term had only a word called rat, so it is 0. So likewise, you can list all the words in the document and number of occurrences of that. And now you see the frequency, document frequency. Basically, this is so the first word cat occurred 2 times, runs occurred 2 times, etc. Rat occurred only once, and dog occurred only 1 times. And then I calculated log n. So n here is 2 divided by this term. So I get these values. And now I calculate TF IDF. So TF IDF is basically the multiplication of TF term frequency and inverse document frequency. So I get these values. Right? So now what I have done is basically I try to map the text documents in a vector space. So let me call it as a document space, right? Document space. Now each document basically is representing a vector. So document 1 and document 2, and even query term also is a document now, or a vector, right? So now once it is mapped to a vector, it's very easy to apply some operations that we are familiar with linear algebra. Basically, now I just wanted to calculate how far this document 1 is from query and how far this document 2 is from query, right? So as you know, you just take a dot product of that or a cosine similarity of that, and you can compute the angle between these two vectors in terms of the query, and you can determine which document is basically closer to the query. So you say that the relevant document to the query is greater of similarity score between document and query and similarity score between document 2 and query. So we computed the similarity score with the technique called cosine similarity. So these are very fundamental ideas. The world has changed a lot, and a lot of other new concepts has emerged in terms of, for example, how to compute similarity. There are varieties of ways in which similarity of two text documents can be computed. For example, like Jacquard frequency term, etc. So basically what we have done is we explored vector mathematics on the representation of words. So here we have to make a note of an important point where a computer can understand only numerical words or numerical data. So we actually try to compute the text documents in terms of a computer amenable vector. So once we say we have created a vector, basically the vector can be easily processed by the computer, right? So this is how we apply the idea that we have learned from vector algebra to the actual problem, so classification problem. So this may not be simpler, because as I pointed out in the case of Google, Google has billions of millions of documents, and computing the query against each and all the documents is bit a difficult job. So another set of elegant kind of algorithms are required to do this process. But fundamentally, we wanted to represent the document, or represent the input in terms of some vectors which can be processed by the computer. And once you get the in terms of vector, you can process it using any mathematical concepts behind the linear algebra. So here we have done only a simpler technique, just to take dot products of this. Now, so is it possible to do in terms of images, right? So why not? Images also we can convert into a bag of. So in the earlier case, basically we were trying to classify each and every words put in a bag, right? So similarly here we can do it as a visual words. So you take an image. So this image, you take patches of this image. So there are different varieties of ways in which you can process an image, right? So by processing, what I mean is I wanted to make that image in terms of a vector, right? So now just I take small patches of this, and I just put the patches in terms of a histogram. So based on histogram, I just represent this image as a vector. So a histogram can be represented by this. So another image, similarly, I can. So you have a set of code words. Basically, in the previous example, we had words, but here you have visual words, or what we call code words. Now, once this is there, you can readily apply the vector space model, and you can do whatever computations that you want to do with those vectors, right? So another to highlight the another example in the same line. So these are bunch of images, and basically I just wanted to execute a query. Is there a monkey there in the image, right? So basic processing is you have to take the features, you have to extract the features, and as I told you, there are a lot of varieties of ways in which we can extract features. Basically, earlier computer science people were trying to extract features using a handcrafted method. That means, like we have done in the case of histograms, we come up with some algorithms, so that executing that algorithm on that image, we can get a bunch of features. But nowadays, due to the emergence of deep learning techniques, so this step of handcrafting features is just disappeared. Now machine is able to figure out the fundamental features that exist in the image, from the fundamental form to a very complicated form of the image. A neural network can understand, basically. So handcrafting images actually is a outdated idea. So for example, shift is a method. Pardon me. Shift is a method where hello, is there any disturbance?
No, sir. You can continue.
Okay, fine. So shift is a technique where we can extract features from the and you give this features so that it encodes, and then it builds a vector. From that you use it for classification algorithm, and then you run that algorithm against the image data set, and then you are able to identify whether the images, is there any image with the monkey there, right? So I just wanted to highlight a very important aspect people are working on, basically called embedding. So we have seen a very primitive example of embedding, where we have seen in the first example, we take the number of words and try to map it on the vector space, right? Represent it as a vector. So basically what we are doing is we try to map a kind of, for example, in a sequence of sentences, for example, there might be a connection between words, right? So if you are treating the sentence as independent words, that may not actually pick up the semantic nature of the sentence, right? So there is a correlation between two words appearing in a sentence. So while you are doing an embedding process, that means while you are constructing a vector, so is it possible to capture that semantics as well, right? It's not just bluntly you are representing a code book of images. It's trying to capture if there are any correlation between the objects that appear in the image, if possible, if that can be captured in the vector space, then after maybe applying the machine learning techniques, you can extract those aspects as well. That means the semantic part of the aspect as well, right? So this is very important. So, and one thing is basically you are trying to have a map from a higher dimensional space to a lower dimensional space. So an embedding is relatively a low dimensional space into which you can translate high dimensional vectors. So basically in the first example where we have mapped the documents to a vector format, basically document space is a higher dimensional space. So what do you mean by a higher dimensional space? Basically a document itself can consist of a lot of features, right? So each feature, if you consider as a dimension, then it's a high dimensional data. So we will look into this matter soon. But for time being, embedding is basically a mapping from a high dimensional space to a lower dimensional space so that a computer can process it, right? And another aspect is this also we will see while we are running to the next example, the idea of sparse vectors. So basically if you take a document and try to represent it as a vector format, so you might need only a few bunch of vectors to represent the whole document space. So you might have heard about the fundamental vectors which represents the entire vector space, right? So with the linear combinations of these vectors, you can construct the entire vector space. So once you are trying to map a higher dimensional thing to a lower dimensional thing, it will be a very sparse kind of representation, right? So ideally, an embedding process, it's trying to capture the semantics of input by semantically similar inputs close together in an embedding space. right? So people have written papers on, for example, while embedding, the similar words are tending to come together, or semantically related words are coming in the embedded space very close, right? So another very important aspect is we can reuse the embedding across models. So you might have heard image net. An image net is basically a bunch of images which learned, and now you give an image to uh, classify it. So whether a human face is there or not in this image. So the same image net you can use for classifying a human's face, as well as you can use the same image net to understand a scenery, for example. Suppose you want to write a paragraph based on a picture, right? So a sunset, for example, a sunset, you want to describe it in text. So that aspect also you can learn from the same image net. So an embedding is basically can be used to use across models. So now there are a lot of varieties of embeddings available for experimentation. So word to vec, basically you are trying to map a word to a vector. The entire document you can map into a vector. So suppose you are doing some business related data, entire customer related data you can map to a vector. Suppose you are trying to classify movies, for example. So movie to vector you can do. Graph to vector. So graph learning is also a very important aspect that is coming up. Then gene to vector, protein to vector, etc., etc. You can always come up with if you want to do some domain specific work, then think about if you have a huge bunch of data in that domain. Let's try to first construct embedding so that the whole bunch of data is represented using a vector format. Then you can play with that vector. So for example, if you are very keen in doing a project on law based projects, so there might be a lot of law related keywords, and those things will be there in the document, and the relationships between those words might be there, or documents might be there. So you can think of law to vec, for example. I'm just giving a very blunt example of another embedding. So law to vec can be another vector which can be used in the profoundly used in the law domain, right? So now you see another example of embedding. So basically, this is this example we will explore more later. So here, what I have done is, so in earlier example, I was just trying to capture the words in the document and try to map it into a vector. But now I wanted to map the movies. So now the dimension is 2-dimension. Basically, we have this axis which represents this side. The negative values represents the children, and the positive values represents the adults. And this in y-axis you have blockbuster type of movies, and maybe some art related movies are in this negative direction, right? Now you put all the movies maybe collected from let's say Netflix, and you try to position it in terms of the features that appear in the movie. So what could be the feature? For example, this movie Shark, right? It's purely maybe for children. So the position of this movie in this two-dimensional space will be somewhere here, or another movie for adults. Basically, this comes somewhere here. So some numbers represent the position of these movies. So you can think of adding more. So basically, what we have done is we have done uh, processing of movies in terms of the taste of children, taste of adults, or the type of movies, whether it is a blockbuster or art house, right? So a typical recommendation system, basically we will touch upon that example later. A recommendation system, basically you are subscribed to Netflix. So while you are watching a movie, so the Netflix, the algorithm behind will try to match your taste and try to give a pop-up of okay, this movie has been released, or that might interest to you, something like that. And most oftenly, interestingly, most of the recommendations are now getting improved. So machine learning algorithms learns these dimension values. So these are features basically, without knowing that they are factors relevant to adults versus children, or blockbuster versus art house. This is also a point you have to note down. The machine learning, so we are not doing this in terms of, let's say, handcrafting. That means we are not trying to classify all the movies based on children, but machine is being trained to learn all these aspects. So all the features, basically, the machine is supposed to learn, right? So now we are ready for talk about something on dimensionality. So already I have mentioned one-dimensional data and maybe a two-dimensional data. Now we talk about dimension in most of the data science related problems in terms of features. So so you have, let's take a medical record, right? And let's say n number of patients and their medical history in terms of their medical conditions, right? So you can just imagine as a table where rows represents each patient and columns represents basically the medical conditions. So these medical conditions are basically the features which represents the entire data. So once we increase, that means once we have more number of features or more number of columns, actually we are going to touch high dimensional spaces. So here the dimension means features. So as and when features increases, the dimension will increase. So we haven't yet seen the phenomena, basically the concepts regarding, for example, in the Euclidean space. We are actually exposed to Euclidean space, and we have a notion of, let's say, the distance between 2 points, right? So this notion of distance between 2 points may not be applicable to high dimensional spaces. The whole concept of, let's say, the volume may not be the same in high dimensional spaces, right? And we are dealing with a huge amount of data with lot of features. So trying to understand the aspects of dimensionality is very important, right? Usually we use dimensional reduction techniques. Maybe you might have heard SVD, for example, support maybe PCA, for example, principal component analysis, singular value decomposition, etc., to reduce the dimensions. So why we wanted to reduce dimensions? So this is very important. So let's see what is the curse of dimensionality. So let's talk in terms of a problem. So we have a a very simple problem where we want to classify cat and dog. So this is very simple. And now we have a bunch of data. So which is basically I collected some data regarding cats and dogs. And let's say I just collected the data based on one feature. So what could be a feature here? It could be, let's say, the weight of the cat or dog, or the color of cat or dog, right? So now I have only one feature. That means I have only one dimension. And how you are going to classify this, right? So from this distribution, you can see that maybe I don't find any way to classify this. So now I wanted one more feature to be added in the problem so that I can represent it in a two-dimensional way, right? So now maybe you can devise a method where maybe let's say a regression, a linear regression kind of stuff. You just wanted to plot a line, right? And check whether how far the feature points are from this line, and maybe you can find out an optimal kind of a line where it is able to classify that cats and dogs, right? Now let's see whether we can improve. So this is an approximate, or maybe we are not able to actually classify it. Now we added one more dimension to this, right? So now it's a three-dimensional kind of a thing. So now points are plotted in this box, right? Now hopefully we can find a plane. So here we are actually finding out a line, but now here it's a three-dimensional object. So a two-dimensional hyperplane can be found out, and you can classify this, right? So this is a well-known problem. Let's see. Okay, yeah. So this is basically I found out a plane where I can easily classify all the instances from one side to other side, right? So more features of what is the lesson here? More features, better classifier performance. Why I'm telling this? Basically from feature 1 to 2 to 3. So when I reached 3, maybe I was able to classify it in a proper way, right? But when you increase the number of features, basically there is a problem called overfitting. So overfitting is basically each and every objects in the data set you want to identify, right? So that they are well classified, right? They are well classified. That means you have a very complicated boundary which classifies all the instances. So while training, this is this is okay because you are trying to classify the objects. But now training is actually not enough. We want to test the system. While in machine learning pipeline, basically you take bunch of data, then train it so that a model is being built, and then you test with some data so that the machine was not exposed to that data yet, but you expose now and see the performance. So in this case, if you use more and more features, right? So more and more features are there. It draws a very maybe complicated boundary to classify the instances. But as and when a new instance comes, it finds very difficult to classify it, right? So here in the previous example, if a line comes, let's assume that dogs are this side, and cats are this side. So I just plotted a line like this, right? Right. So there are some exceptions here, but maybe when a new cat comes, maybe I can easily put that cat here. When a new dog comes, maybe I can easily put in this side. But when you increase the number of features, you will find difficulty here, right? So even though classifier performance is better when features are increased, but there is a problem with overfitting. So, and you cannot generalize so the core aspects of data science related algorithms they must be generalizable. That means for any unseen data, it must be performing in a better way, right? So here is a plot where you have a classifier performance and the dimension. So as and when you increase the dimension, the classifier performance falls, right? So increase of dimensions are not that much good. That might be one reason you go for dimensionality reduction, right? So let's look some more details of this problem. So how much training data is required for to teach a machine learning algorithm, right? So let's assume that I have 20% of training data here, right? So to cover the entire population of cats and dogs in one dimension. Now, if you increase the feature, number of features are increased now here, 2. Then we need 45% of data for each dimension in 2 dimensions, right? And when in 3D, you have 58% of data in each dimension in a 3D. So that means as and when you increase the dimension or features, you need more and more data to learn the classifier, right? So that's why people say usually in machine learning, you need a huge bunch of data to learn a classifier or any machine learning related algorithms, right? So let's see what is the implication. So let's when the amount of available training data is fixed, then overfitting occurs. And when we keep adding dimensions, and if we keep adding dimensions, right, the amount of data that needs to be trained is growing, right? So it grows exponentially basically. So we have seen in 3D also, 3D, but I will show the plot where you need more and more data. So the requirement of data actually exponentially increases. So the curse of dimensionality introduces the sparseness of the training data, right? The space is huge and you need more and more data to tackle the problem, right? Then the more features that we use, more sparse the data becomes, such that accurate estimation of decision boundaries becomes very difficult, right? And this sparseness is another very tricky kind of a statement. A sparseness is not uniformly distributed over the search space. So even this diagram might be a little bit misleading. I have shown that most of the cats and dogs are evenly distributed, but this is not the case. So we'll see that in a moment. So to understand this curves of dimensionality, we have to go and check basically a very important concept, volume of an N ball. So a ball is a region in space comprising of all points within a fixed distance from a given point. So basically you have a circle inscribed inside a square, a unit square. So N ball is basically an n-dimensional, a ball in n-dimensional Euclidean space. So we call it as a hypersphere. So I have demonstrated here a 2-dimensional version of that. So most of the time, the average features. So I have created a square, a unit square, and a unit a sphere or a circle is inscribed in this, and I have data has been distributed within this, and most of the time, the average of features are concentrated here. So since you have a unit circle, and all points within the unit distance from this center, so that average comes at the center. The unit square that represents the 2D feature space. So classifier will find difficulty in classifying the points near the corners of the features, right? Corners of the square, because you are averaging or you are comparing it with the averaged value of the feature, and you will find out difficulty in classifying these instances. So now let's ask a question: how the volume of the circle or the hypersphere changes relative to the volume of the square or the hypersphere. So when we increase, when we, hello,
Hello. Yes, sir.
there is a disturbance. So when we
Yeah,
increase the dimensionality of the feature space, what happens?
1 minute. 1 minute, sir.
ஆறாது
Somebody has to mute the mic. Shall I continue?
Yes, sir.
Shall I continue?
Yes, sir.
Okay. So what we were trying to see is we have a hyper cube and a ball of unit volume is inscribed in it. And when the dimension is increased, the volume of the hypersphere is increased, what happens, right? So you can see this in this graph. As you increase the number of dimensions, the volume of the hypersphere goes down. Even after maybe a few bunch of number of dimensions, it goes to 0. So this formula will tell you that. So when dimension goes infinity, the volume of the hypersphere goes to 0. So what does it mean? So basically, let me just illustrate this with some few dimensions. So this is 0 dimension. This is 1 dimensional. So volume of the ball. So this is 2R, and this volume is 0.5 multiplied by the volume. And in 3 dimension, you have this 3 by 4 V pi power 1 over 3. So this is proportional to V to the power of square root of or root of something, right? So as the dimension increases, the volume goes down. So volume of hypersphere tends to 0 as dimensionality tends to infinity, whereas volume of surrounding hypercube remains constant, right? So what does it mean? So when the dimensionality of the feature space goes to infinity, the ratio of the difference between minimum and maximum Euclidean distance from the sample point to the centroid and the minimum distance itself tends to 0. So let me just use a demonstration. So I have a Python code where this code basically generates some random points inside a cube, right? And finds out with respect to one point how far the other points. So this is what is been done. So can you see the code?
Yes, sir.
Okay. So what I'm trying to do is I randomly generate points in a cube and try to find out how far the points are. So you see that when the dimension is low, so this is a sphere in a 3 dimension. Most of the points are equally distributed, right? And when it is in 30 dimension, you can see the pattern is actually been changed. When in 300 dimension, you see that most of the points are actually converging to the expected value. That means the notion of distance between 2 points, maybe you cannot distinguish 2 points maybe from the other pairs. All are maybe equally spaced. So that is the point I just wanted to show you from this code, right? So the notion of distance is different basically in n dimensions. So you see in this diagram, basically as dimensionality increases, a larger percentage of training data resides in the corners of the feature space. So as I told you, the distribution of the points are not actually even. Most of the time, the data appears at the corners of the feature space, right? So this is in a hypercube, and maybe the distribution of the data. So at the edges of the cube, basically the data is being distributed from the average. So that means the distance is actually almost same. If you take any point and measure the distance from the average, it will be almost same. So any questions so far? Maybe I just wanted to interrupt.
So the question session would be after the lecture.
Okay. Otherwise, the entire show will be.
Uh,
So I can take some 20 minutes. Right?
Yes, sir. Yes, yes.
Okay. So I will go quickly from here. So what we have done is basically we wanted to map some high dimensional data sets to a lower dimensional data. And basically we call it as a manifold learning. And what we are doing is basically we try to find or learn non-linear relationships among the dimensions or features. And Euclidean, the notion of Euclidean distance measure is meaningful only local. So if you have a bunch of data, maybe you just concentrate on local patch of that data, then you can apply the notion of Euclidean distance, but not in the entire global aspect. You cannot apply that. So the reason is actually I have just explained to you. Now we wanted to classify points which are not basically linearly separable. That means the data points are not maybe with a line you cannot just classify them. It's a complicated distribution. Now you see here the second diagram. So these are data points, and what can you say about the distance between this the point A and point B, right? So this is a data maybe appearing in a high dimensional data. You can visualize it, and you can rotate it, and you can see how the points are actually been even in a 3 dimension. You can try to visualize it, and just to rotate it and see what is the concept of distance of the point A and B, right? So if you locally compute it, basically the A and B are actually coming very far, basically, right? And there is no point in so for example, suppose you are suppose you are clustering the data. So this data point, let's say with color, I can understand some 1, 2, 3 clusters you can see, and there is no point in putting this point in this cluster, right? So they are semantically different. Actually, they are far away points, basically, right? But if you are trying to apply the Euclidean concept of Euclidean distance, then this will be the classifying this point in this cluster will be wrong, right? So what you can do is you can locally compute the distance, and maybe you can find out A is very far from B, right? So that basically you can do a kind of an idea which is called diffusion mapping. So diffusion is basically introduced from physics, basically how heat is basically transferred from one end of a metal to another end. Basically, it pertains to the continuous domain, but now we just take it for a discrete domain. So diffusion map, basically you define a graph, and you define the process as a time-dependent diffusion process, right? So I will illustrate that. So all the points are actually been mapped to a graph, and you execute a random walk from one point and try to identify how far the points are. So basically, you can define a matrix which is called a diffusion matrix P, which is basically a transition matrix, which you might be familiar with the Markov modeling, Markov process. So same idea, but we call it as a diffusion matrix here. And if you power iterate this P, you can find out 1 hop, 2 hop, 3 hop distances from a point. So basically, power iteration is you take the P matrix and multiply by itself. You get the second hop, P square. Third hop, or P cube, will give you the third hop, etc. And finally, you will see that the matrix, you cannot just go infinitely. The matrix will be finally converged to some values, and there won't be any change happening in that matrix. Then at that point you can stop, and you can see a stationary distribution you can see, and you can find out the distances from one point to another point, but applying the notion of local computation. So basically what we have done is a local computation. So the local computation notion is coming from a random walk problem. Basically, I associate the connectivity with the probability of my neighborhood or connectivity. So starting from 1, what is the probability that I can jump from 3, 2, and 4? Some probability you can associate with that, right? So while you are running that process, you can compute the distance from the points locally, right? So similarly, spectral clustering is another technique where you can utilize a simple concept to cluster different data points. So if you apply a classic kind of an method, classic kind of method may not be applicable to these type of distributions, because this is not linearly separable. So basically the point is you are trying to map the higher dimensional data in a lower dimensional manifold. So that's why it's called manifold learning, basically. So here also I just use a idea of graph by an idea called spectral clustering. So where these points are so this is an example of a graph where I have weights associated with the graphs. I can maybe assign a Gaussian distribution to have a similarity score between the points and weight them according to that. So a adjacency matrix for this graph, basically Aij is 1 if the points are very close, and Aij is 0 if the points are far apart. So this adjacency matrix you can construct from the given matrix, and then you find out the embedding. Basically, we are trying to map the points from higher dimension to lower dimension, and that can be done through a Laplacian. So basically, a graph Laplacian is defined like this. So this is basically a matrix which represents an degree of a vertex. So this gives you the degree of vertex, and you make a difference from the adjacency matrix that you have computed, and you can compute the L matrix. So L matrix can be computed from here. So this is the graph Laplacian. So the D is basically represented as maybe sum of the weights. So that is being replaced for the diagonal elements. So this is representing L. Then you compute the spectrum. Spectrum basically you can compute using the eigenvalue, classic eigenvalue problem. And now you see you can compute the different eigen values and corresponding eigenvectors. So here basically the lambda 1, this is the lambda 1 will be 0 because we are trying to find out the connectivity of the graph. So once the graph is fully connected, that means you don't have maybe sub graphs. So that will lead to this lambda 1 is 0. Now you concentrate on lambda 2. So lambda 2 will represent the connected or the components of the graph, right? So if G is connected, so lambda 1 is 0 and lambda 2 is greater than 0, and we call it as algebraic connectivity of G. And if lambda 2 is greater, then there will be greater connectivity. So this is an example of computing eigenvalues. And you create a cluster. Basically, the eigenvector corresponding to the second eigenvalue is created. And based on that, you can map it to the graph. Basically, what are the nodes basically having these type of weights? So that comes one side and the other comes the next side. Based on that, you can apply a cut and you can have a graph cut kind of a structure here. You can apply the graph cut algorithm there, and you have different clusters here, right? Now you can run the classic k-means algorithm and you can find out different clusters. So one more problem I just wanted to highlight is a Netflix price problem. So it was a problem of worth $1 million. This was announced in 2006 also. So basically Netflix has a lot of movies and a lot of customers, and they wanted to come up with an algorithm which will do a recommendation engine which does a 10% more accurate than the engine that they were currently using. So how we can attack this problem using a idea called matrix completion. So assume that you have a huge table where you have rows as number of users basically who watch the movies, and in the columns you have a lot of movies. Basically, as I pointed out in the previous examples, movies could be referring to a lot of features. So some features I just highlighted here. It will be a comedy or action, and the user whether he likes comedy or action. So based on that, you can. So this is a huge matrix, and your goal is to compute these sub matrices so that once you multiply this, you will get this. And interestingly, this matrix will not be a complete matrix. You have a sparse matrix here. So most of the users might not have rated. So these numbers are basically representing rating. So 1 rating means low rating and 5 means a higher rating. So most of the columns, most of the cells may not be having values because most of the users might not watch all the movies, or they might not be interested in rating movies. But Netflix wanted this matrix to be completed so that they can find out which users are or users' preferences are similar, right? So I might be interested in a comedy kind of a movie, for example, and some kind of action is also. So there could be a lot of other persons who like this, right? So when my preferences are being computed, maybe based on that preferences, the other similar persons can be recommended similar type of movies. So that is the core idea. So here basically this is factorization problem. You can find out factors, right, and try to fill out the matrix. So how we can do this? So this is the actual size of the matrix, and we have this is a sparse matrix with this much of entries, 2.1 billion of entries, and you wanted to compute this, right? So this is the problem. So basically how we are going to tackle is you generate randomly these two matrices with the available data that is there in the sparse matrix. Randomly generate some values and try to maybe compute the dot product between these elements and find out what is the corresponding value appearing in this matrix. And based on comparing the error, that means you computed something arbitrarily and comparing with the results that you want. And if it is far away, maybe try to adjust the values here or here and then recompute it and again find out. So finally, you can come up with an optimal value. So this is the idea. So this is basically a mean square error you wanted to compute. So this is a classic, maybe in linear regression, you might have studied this. So what is expected, and so this is the rating given, and you compute the product of this, and you compute the square of that distance, and compute how far you are. And this must be some regression, maybe penalty terms that you want to regularize the learner. So regularization terms can be also updated like that. So this is the algorithm suggested, alternating least square algorithm. So basically the total matrix R is represented as U transpose V, where U is the user and V is the matrix representing the movies, right? So you approximately compute R. So this is the algorithm. So alternate between U and V computation, and finally find out an optimal value for R. Okay. So I think I don't have much time to go ahead. Just maybe this slide is basically for streams of data. So far we were actually trying to explain about a collected bunch of data, but most oftenly data is not there for our use. Most of the times data is coming as streams, right? And there is no possibility of storing all the data, because maybe we need terabytes of memory to store that. But is it possible, as and when data comes, right, can we figure out something from that and leave the data, right? So this is the classic kind of data stream algorithms. Heavily depends on the probabilistic and randomized algorithms, and basically you wanted to create some sketches from the available data, and maybe there are a lot of sketching schemes which gives you a summary of whatever you have seen so far, and based on that you make a decision, right? So there will be a query coming, and you have to make a decision based on the sketches that you have collected in the memory. And why you want this? You want sublinear algorithms, because you have a very limited amount of memory. Within that, you have to create a summary of the data and give answers for the questions. So for example, suppose a stream of numbers are coming, right? And I wanted to say what is the average of the numbers that I have seen already, right? So what is the current average, right? So that needs a lot of maybe tricks and techniques to compute. So there are huge problems there in data stream area. Those who are interested can just explore data streams, because most of the data is coming as streams, like in IoT, in networks. Most of the data are coming as streams, and you can try some of the algorithms to figure out something interesting from that. So I just maybe conclude because my time is over. So data science is emerging as an independent field. Maybe this is a bold statement, because if it is qualified to a independent field, it must be having fundamental maybe ideas contributed in that field. Maybe that yet we have to see, but it's emerging as an independent field. And data and computational aspects are very crucial. Most of the machine learning and deep learning techniques are emerging and contributing a lot in the data science area. So to conclude, what I tried was I was trying to give you an positioning the mathematical aspects of data science. So so far what we have done is we have seen the importance of embedding. Basically, to process something by the computer, we need a representation, and we can use the idea of vector space there once you get in terms of vectors, right? Then the idea of manifold, basically we want to represent the data in a lower dimensional space to deal with the data. The third aspect is the concept of distance, or the volume, or the even the surface area may not be the same in larger dimensions. So that needs an attention while you are processing data. But there are clever algorithms where you apply it locally, so that we can solve the problem. Where locally still the Euclidean concept is valid, and we have seen a bunch of examples there. And finally, we just mentioned that streaming is an upcoming area in data science, where there are huge opportunities for even for probabilistic kind of learning, randomized kind of an algorithms. There are a lot of scope for that. So with this, I just want to stop for possible questions.
Yes, sir. Thank you so much for the great insight about the mathematic perspective of data science. We got to hear new insights of data streaming, document representation by a vector, and the vector math on a representation of words. So it was a great session, sir. And over to Minu for question session. Participants can post their questions.
Thank you, Meena Miss. Sir, one question.
Yeah.
Where does the exact borderline exist in
Borderline between?
Where does the exact borderline exist between ML and DL?
Okay. So basically, maybe I will highlight the one maybe superset, which is called artificial intelligence. So machine learning is basically a bunch of algorithms which is used to teach a machine with a lot of handcrafted features. As I pointed out in my presentation, a lot of handcrafted features are required to learn some of the algorithms like classification and clustering, etc. But unfortunately, most of the data that is available to us is maybe unlabeled data. That means we don't have labels attached with the data. So in that scenario, basically constructing a feature from the data is very difficult, right? So people come up with a lot of ideas where a neural network, basically maybe neural networks were there in 1970s, but a relook of neural networks just recently happened in 2012 onwards with idea of deep learning. Basically, earlier we had one neuron which tries to learn something from the input. Right now we have a lot of layers of neurons where neurons tries to learn something maybe hidden from the data by itself. So basically, deep learning is one of the subfield of machine learning where these type of automated kind of algorithm and learning mechanisms are applied. So once you say deep learning, definitely belongs to machine learning technique, but the difference is basically you are not concerned about the maybe even there is no need to look at the data. You just take the data, clean it, and then feed it to a neural network related engine, so that it tries to learn by itself and gives you output. So machine learning, then a subset of that is a deep learning, basically. Yeah.
Sir, next question. Which vector spaces are mostly used in data embedding?
Yeah,
Space of
I
column
think
vectors.
I got a question from which vectors, I think Anup Nair.
Yeah.
Anup, can you just, or maybe I will read the question and answer. Which vector
Uh,
spaces are mostly used in data embedding?
Space of
Space of column vectors, space of matrices,
matrices.
or polynomial space, or something else. Okay. I think based on the features, we talk about the embedding, basically, right? So even you can take the entire document and you can build a embedding space. So which we call doc to vec. So document, once you take the entire document, you actually try to see what kind of features are actually representing each and all documents in the space, right? So depending on the features, you have to embed, right? And uh, space of matrices or polynomials is basically a vector. Basically, the outcome of embedding is a bunch of numerical values, and you call it as a vector. Basically, these vectors can be used to learn maybe further stages of the learning process. Then what is this? IDF log. Okay, to deal with maybe numbers, we usually take logs, right? Because we wanted to deal with huge numbers, for example, or smaller numbers. If you take log, you can easily handle those numbers. Which are the optimum. Basically, in machine learning, the optimum is depending on the consumer who wanted to write the algorithm for his business, for example. At one point, the consumer or the customer actually wanted to, maybe I want this much accuracy, right? So 98%, for example, of customers' data I have collected, and maybe I learned something, and my classifier gives a 94% accuracy. That means if it is okay for his business, then he can stop there. There is no need to further optimize the algorithm. Depends on what kind of scenario you are going to apply. Depends on the maybe the optimum values, right? So if you are doing a medical related stuff, maybe we expect 100% maybe result, but maybe and from 99% result or accuracy, we may have to stop, right? So another question is, let me answer all these questions. Do we have to define distance according to the characteristics of the data in definitely, yeah, definitely. So usually people tend to use Euclidean distance as a norm. Uh, Based on the machine learning accuracy and those things, you can try with different norms. Basically, there are L2, L1 norms are there. There are a lot of regression, regression kind of techniques are there to define the norm that is required for your problem, right? Is non-negative matrix factorization one of the decomposition possible? Maybe. What is this question? Basically, we are trying to find a low rank matrix while we try to factorize it. Negative, I don't know. I actually I don't know.
So another question.
Basically, what is meant by cleaning data? Cleaning data is basically, as I pointed out in my talk, suppose you are taking HTML pages for processing your data. So HTML tags itself is not necessary to process the data, right? So HTML tags, everything you can write a program and just delete all the HTML tags. So that is one kind of cleaning. Maybe all the stop words, etc. Those words you can remove from the data if you are dealing with the maybe a text data. So this is what is meant by cleaning data, right? So if you are not cleaning, it will affect the your algorithm, learning algorithm. Sir, what does tools like TensorFlow exactly do in machine learning? Yeah, it's a very good question. TensorFlow is basically a tool developed by Google, and it made available to all the users. So if you want to write a machine learning algorithm for your problem, most of the algorithms, fundamental algorithms already implemented and available as a library, right? So in a Python code, you can just call one of the function from that is available from TensorFlow, and you can execute your algorithm. And TensorFlow are actually heavily optimized for your process, right? TensorFlows are basically there are tasks which uses GPUs. You might have heard graphical processing units than CPUs, our ordinary processors. So GPUs are very heavily used for processing images. So TensorFlow related libraries and framework is actually optimized for these type of workloads. So there is no need to maybe reinvent from the scratch how to optimize a simple function. So if it is available already, then you can utilize it with the TensorFlow framework. And there are a lot of other frameworks available. Not only TensorFlow, there are a lot of other Keras is available, lot of PyTorch is available, lot of frameworks are available for the programmers to make their life simpler.
Sir, Vijayama sir is having a question.
Data, do we actually reduce the system to techniques that are employed in stored data? Or is there a specific algorithm or methods for the streaming data? Definitely. As I told you, our goal is to find an algorithm. If you are looking at it in the algorithmic way, we are trying to design suboptimal algorithms. That means sublinear algorithms. That means of the order of n is not enough. We want an algorithm which is running of the order of log, right? Because we have a small amount of memory. Memory in the sense it is while processing, you are talking about the RAM memory, and we have a very small space there, and we want to process the data before it disappears, right? And we don't want to store it again. So whatever patterns that are available in the data, you pick it as and when it is exposed to you, then leave it, right? Like a running stream of river, for example, you are given a window to look at one window where you can see the river is flowing, water is flowing, but the same water you will not see at the maybe in a different time interval. The amount of water might have already passed. So whatever information that you want to extract, you extract from that there, right?
Sir, Vijayama sir is having a question. Vijayama sir, please unmute your audio.
Yeah.
And you can ask question.
Is it audible?
Yes, sir, it's audible.
Hello, is it audible?
Yes, sir, yes, sir.
Yes, very much.
Okay, Santosh, you mentioned about algebraic connectivity.
Yeah.
You mentioned about algebraic connectivity. We are working on spectral graph theory. That's why I'm asking this question.
Okay, sir.
Algebraic connectivity is actually the least positive eigenvalue of Laplacian.
Yes, yeah.
What is the significance as far as data science or your parlance is concerned?
Sir, basically in the given problem, I was trying to illustrate how you can separate, maybe how to cluster non-linearly separable data. If we are trying to directly solve the problem, I don't think the methods are enough to solve that problem. So what we wanted to look at locally, in terms of the neighborhood, right? Who is my neighbor? And based on that neighbor, you build up a graph and build up the notion of how far you are from the other nodes. So once you compute a spectrum of graph, you are actually exposed to the connectivity information from the graph. So the eigenvalues gives you the connectivity information, and based on the connectivity information, you can now maybe let's take k number of eigenvalues and try to cluster it into k clusters.
Okay, I think I will better ask offline later.
Okay, sir. Okay, sir. Okay, thank you.
Okay, okay. Yeah, please go on.
Yeah.
So next question, how to perform complexity analysis for machine learning based on time or space?
Basically, you perform complexity analysis on the algorithms that you actually contribute, not on the entire machine learning pipeline. In machine learning, basically, you are trying to get the accuracy or other measures. For example, if it is a information retrieval problem, what is the recall or what is the precision, etc., etc. But definitely you are concentrating on some of the algorithms that you are written for doing some purpose, right? So you have not written a whole bunch of algorithm or a single algorithm to solve the entire problem, right? So whatever algorithm that you contributed, there is a way to compute complexity of the algorithm in terms of space or in terms of computation complex speed, right? I hope maybe I answered that question.
Sir, next question. There are distance formulas other than Euclidean formula. Example, in terms of inner product space, how to decide which to use?
Depends on the problem that you and the embedding that actually you wanted to define for the problem. You can very well try. Basically, see in linear regression, for example, basically we take the square of the distance, right? And we wanted to optimize based on that. So similarly, you can try with other possible distance formulas with the. So it's an optimization problem, right? So you try with and maybe come up with better results, and that depends on the problem as well. Yeah.
What mathematical background is mandatory for machine learning and deep learning?
I think this FDP, I think elegantly covered whatever required for dealing with machine learning and deep learning stuff. Basically, a better understanding of linear algebra is a must, right? That is first thing. Second thing is the idea of probability and maybe a probability related stuff, idea of randomness, etc. So that is important. And third one is the optimization part. Optimization, how cleverly people write algorithms to optimize things. And I think if you have a very good notion of or good understanding of these aspects, it is good enough. It is good enough to enter into the machine learning and deep learning arena. But maybe nowadays people trying to tackle the problem and then learn maybe the underpinnings. That approach will be maybe good because we have very limited time, and we straight away go to a machine learning kind of a stuff and try to understand what is the problem, and then try to identify the algorithms, the core algorithms behind that, and core mathematical aspects behind that. That will be a better approach rather than you learn everything and then jump into the deep learning pool. You jump into a pool and understand the heaviness of the pool and then try to figure out whatever things you wanted to learn. Yeah.
Okay, thank you, sir. And I think there are no more questions.
Okay.
Now over to Minamas.
Yeah. Very,
Minamas.
yeah.
Yes. Thank you, Minu. And sir, once again, it was an excellent session. And we got to know how the mathematics plays an important role in data science. And thank you for your presence virtually. Thank you so much, sir.
Yeah. Okay. Okay. So on behalf of maybe my department, I just wanted to thank the authorities of your college for inviting me for this session, and I thank all the audience. Audience were very maybe uh, curious about knowing a lot of things. I think I tried to answer most of the questions, but if you have further questions, you can always uh, contact me through maybe my email ID. I will just write it here. san@qsat.ac.in is my email ID. So you can drop me mail if you wanted to get any more clarifications on this. Right? So thank you so much.
Yes.
Thank you, Vijay Kumar sir, for introducing me uh, this college and introducing me to Meena. Thank you.
Yes, sir. Thank you. Thank you, sir. So now having come to the last day of our FDP, let us now move on to a small valedictory session. With great pleasure, I invite our Vice Principal of Muthoot Institute of Technology and Science, Dr. Chikku Abraham, who has been an instrument, has always been an instrumental part in our progress. So I request Dr. Chikku Abraham to take over and say some words. Sir. He will be joining us rightly. Okay, I think he has got some administrative work. So we will move on to the next session of before moving on to the concluding part of our validity. I first of all like to invite ask if the participants have could share their suggestions on this forum. Participants can unmute. Participants. Okay, if there is nothing from the participant side, um, any words from our resource persons? Um, 1 minute, our vice principal has joined to give his felicitations. So over to Dr. Chikru Abraham, vice principal of MITS. Please,
Yeah, ma'am,
sir.
is it audible?
Yes, it is audible. Yes,
Is it
sir,
audible,
it is
ma'am?
audible.
I hope I'm audible. Hello?
Yes, it is audible.
Yeah, I had a connectivity issue.
Okay,
Uh,
okay, sir.
am I audible once again?
Yes, sir, you are audible. Yes.
Yeah, thank you. Good afternoon, everyone, and greetings from MITS. I'm very happy to note that the Basic Science Department has conducted, the Basic Science Department has conducted a very wonderful FDP, and we had a very great resourceful, starting from Dr. Vittal Ravu to Dr. Vijay Kumar sir to Dr. Asha ma'am, Dr. Murali Krishnan sir, and finally Dr. Santosh Kumar sir. The artificial intelligence and the other one in cyber security, and we have one additional new BTech in AI. So we are developing our capacity here, as well as we are looking into more competency to develop in our space also. So I'm very happy that there were more than 200 participants in all of these FDP sessions, and I would like to personally thank Dr. Santosh Kumar, professor in yeah. I would like to thank Dr. Santosh Kumar sir for taking his time and giving a wonderful insight into the mathematical applications and data science. And I congratulate the entire Basic Science and Humanities department for the great program that you have conducted in the last 4 or 5 days, and all the participants. The take home, we at MITS feel that it was very informative and will open more and more curiosity in your research and understanding. Thank you once again, and wishing you all the best. Thank you, ma'am.
Yes, sir. Thank you, sir, for your good words. And now it's over to the coordinator, Jinsi P. Matai, to give the thanks.
Thank you, Meena ma'am. Good afternoon to all. Today, we have come to the end of the 5-day faculty development program on mathematics for data science. On behalf of Muthoot Institute of Technology and Science, I take this opportunity to express sincere thanks to our Executive Director, Sri George Varghese sir, who has been a great source of inspiration throughout our program. I express my profound gratitude to our esteemed principal, Dr. Neelakandan sir, for his consistent leadership and guidance at full length. I thank our honored Vice Principal, Dr. Chikku Abraham, for mentoring us in all our academic activities. I would also like to thank our beloved Head of the Department, Dr. S. Shivakumar sir, for his moral support and guidance. I profusely thank our distinguished resource persons, Dr. Vittal Rao sir, Dr. Vijay Umar sir, Dr. Asha ma'am, Dr. Murali Krishnan sir, and Dr. Santosh Kumar sir, for enlightening and captivating us with excellent insights in the arenas of data science and making this faculty development program informative. I would also like to thank our electrical and electronics HOD, Dr. Jani Das, for her impelling support. This event wouldn't have been successful without the participants. Thank you, dear participants, for your efficacious participation and valuable suggestions. Last but not the least, I extend my sincere thanks to all my colleagues for their active participation and great support through the entire program. Thank you all for making this event a grand success. Hoping to meet you again in the near future. Stay home, stay safe. Thank you.
So, having concluded our sessions now, it has been a short journey together, and I appreciate the enthralling participants for the good support, and also a word of appreciation to my team, without which we wouldn't have conducted this excellent session. And the feedback link has been shared, and you will be getting your e-certificates within 2 days. So thank you once again for all the participants and the resource persons for the grand success of our FDP. Thank you, sir. Thank you all.
Thank you, madam.
Yes, thank you, sir.